Alrighty. Hi, everyone. Living my best hoodie life today. Fourth video today. Here we go. Today, we're doing equilibrium. Even though for me, it's the fourth thing we're doing today. For you guys, it's the first thing you're doing today. Don't get ahead of yourself. Do one lesson a day. Equilibrium, you probably know the word. It has something to do with balance, right? I sound like Dora asking questions to myself. So we can talk about equilibrium in a few different contexts. I'm focusing on chemical equilibrium here, but I will also touch on the others. So here you are. You're riding a bus. You're riding a bus and there's 30 people on the bus. All right. Now the bus stops. 5 people get off the bus, but now 5 new people come on. How many people are on the bus? Should I just blink like Dora? Right, it's 30. This feels so dumb. I miss you guys. Yes, there's still 30 people on the bus. What has happened is that the individuals on the bus are different people. Their identity has changed, but we still have the same number of people on the bus, and that's essentially chemical equilibrium. It's a tiny bit more complex than that, but that's the gist of it. Oh, this darn bubble. Okay, so there are 2 ways that we can describe chemical equilibrium. The first is that the concentrations of my reactants and products remains constant. Concentration, remember, is a fancy word for the amount of stuff. So the amount of reactants and the amount of products is going to stay the same. Okay, we can relate that to the number of people on the bus being the same. If 5 people get off and 5 people get on, we still have 30 people on the bus. That number is constant. We still have 30 people on that bus. We can also say that the rate of the forward reaction and the rate of the reverse reaction are the same. So 5 people got off, 5 people got on. That's what I'm talking about. It's 5 both times. If I had 7 people get off, but only 2 people get on, I would not have 30 people on the bus anymore. If 7 people got off and 2 got on, we would be at 23 plus 2 is 25. We'd have 25 people on the bus then. That would not be equilibrium because we're not balanced, okay? So in this case, if you think about a chemical reaction, like we were talking about with the table I stuff, you can flip reactions and do them backwards. This would be the reaction going from left to right is happening at the exact same speed of the reaction going from right to left. So they're like, woo. They happen at the same rate. Okay. Next slide. Yes, this is somebody on not a skateboard. They're balancing because equilibrium is a delicate balance. Okay. A dynamic equilibrium is primarily what we're talking about here. If something is dynamic, it means that it is changing. Like a dynamic character is one in a book that starts off as one way and like learns stuff throughout the story and comes out as like a different personality. A static character kind of stays the same throughout. Dynamic equilibrium is a situation where we have changes happening, but stuff is also staying the same, which sounds kind of crazy, but think of the bus. The thing that's changing is just the identity of the people. We have 5 people get off and 5 people get on, but the part that stays the same is the number of people on the bus. So even though it's changing, it's also staying the same. Okay. There are a few different types of equilibrium. We've talked about 2 of them already. So we have phase equilibrium, which is the transition between phases. So you have solid and liquid. That phase equilibrium would be melting or freezing. And then we also have the phase equilibrium between liquid and gas, which would be, evaporation and condensation. So if you remember from my classroom, we did, I put water in an Erlenmeyer flask and I put the lid on it, and then you got the condensation around the top of it. That was phase equilibrium because my liquid was evaporating and then my gas was condensing at the same rate. And that's why the level of the water never changed. That's what's changing but staying the same. Okay. And then we also have solution equilibrium that we've talked about before. If you have a saturated solution, meaning you have junk sitting on the bottom that won't dissolve, what happens is, let's say it's salt, right? I have a bunch of salt sitting at the bottom of my beaker. I will have one teeny tiny particle of salt sitting on the bottom. It will go into the solution and dissolve at the exact same moment that a little particle that's swimming around in the solution will undissolve and sink to the bottom. So they're happening at the exact same time. One is dissolving and one is undissolving. That's their rates being equal. So the amount of salt on the bottom is always the same. Does that make sense? Changing but staying the same. Now, the new type of equilibrium is the chemical equilibrium, where we have a reaction that goes backwards and forwards. So the most famous, I think, equilibrium reaction would be the Haber process, and that is the formation of ammonia. So let's just throw that in here. We're going to talk about the Haber process. I have an extra credit for you if you're interested. The Haber process is a famous case of chemical equilibrium. So in the Haber process, we have nitrogen gas and hydrogen gas, and I want to insert a special character. I want a double-sided arrow, because we can represent equilibrium in one of two ways. We can have a double-sided arrow like the one I have here, or you can have one arrow that goes left on top of an arrow that goes right. You can do that as well. Here we go. This is balanced, yes. So we have two ammonias on each side, two nitrogens on each side, and 6 hydrogens on each side. And this is a famous case of chemical equilibrium. So if we had nitrogen over here, this nitrogen would have to break its triple bond. Remember, nitrogen triple bonds to itself, and it would, these hydrogens would also be breaking their bonds together, and they would form ammonias over here. But at the same time, these ammonias are breaking apart and forming nitrogens and hydrogens. So it goes back and forth. So really, it looks like nothing's happening. But if you like really zoom in and pay attention, like on a molecular level that you can't see with your own eyeballs, there is something happening. And tomorrow, you're going to learn all about how to disrupt equilibrium and how to get equilibrium back. That is called the Le Chatelier's principles. Those are a little bit of a pain in the tush. I'm just going to be upfront with you. But if you can wrap your head around this, you'll be okay. All right, so recap. Equilibrium, we have people on the bus, 5 get on, 5 get off. We have 30 on the bus in total. No matter, as long as the same number get on as get off, we are in equilibrium, because the concentrations of my reactants and products is the same. So the number of people on the bus never changes, but because the rate of people getting on and the rate of people getting off are equal to each other. If those rates, if one of them happened faster than the other one, like if I had only 5 people get off but 10 people get on, we don't have a constant concentration of people on the bus. Okay, so you need those two things. Rates are equal and concentrations are constant. If you want to go in and highlight this, concentration is constant. Whoops. That would be something to think about, okay? And then 3 types of equilibrium. We have phase, solution, and chemical. And they're all kind of similar in that the rates of whatever is happening, the forward and the reverse, need to be equal to each other. So that's it. If you're confused, watch it again. If you need a little bit more help, let me know in the comments. I will do my best